Alright, so we're going to continue on with some of the basic stuff here with calculus, just so we can get a good background. We are now on the area problem. Now, the first idea was finding limits. The first idea was us taking a tangent line, right, trying to create that by taking 2 points, developing a secant, and sliding that point Q very, very close to point P, almost touching it. And what we realize is when you continue to push things really, really close like that, that was basically what a limit was. So now we are on the second idea that will be in calculus, and that is the area problem. We're going to do a much shorter explanation of this because once we get into like chapter 5, 6, and 7, we're going to really dive into a much better explanation. But this is just to kind of show you what is all involved with calculus, kind of like a quick little synopsis. Alright, so we make approximations to find the area under the curve. Okay, so here's our curve from one point A to another point B, and we want to find the area of all this. Okay, now logically the easiest thing to do, which is what we mainly know, is shapes, right? If I was to draw a straight line here across, we would basically have like a rectangle, and you can easily find the area of a rectangle. But what about all this other stuff that I'm missing? How do we find like curves, right? Well, if we have a nice simple shape, it's kind of simple, but in this case we don't. So the way we really know how to take the area of stuff is by finding area shapes. It's kind of what we learned in geometry. So what we're going to do is we're basically going to use rectangles because the area of a rectangle is simple. It's just base times the height. So what we're going to do is to find the area, right, to make an approximation. There is one rectangle. Obviously that is approximation of the area under the curve because I'm missing this little part and I'm missing all of this. So it's just an approximation, but I could make an even better approximation by possibly having more than just one, right? More than just one rectangle. Maybe I make it better by having like 10 or 12 or 15 or who knows how many rectangles, right? Because now when I go to make my approximation with all of these rectangles, I can find the area of this one plus the area of this one plus the area of this one and so on, and add all those areas together to find the approximation of the area under that curve. And now the approximation went from I'm missing all of this and this to now all I'm missing is this little part here and this little part here and that little part and that little part. So my approximation actually got better of the items that I'm not including in my area, right? Rectangles are an easy area to find, all right? So we chose rectangles to do that, to find the area under the curve. And again, the more rectangles we have, the better the approximation. Why stop at like 10 or 12 rectangles? What if I had 1,200 rectangles? What if I had 12,000 rectangles? All right. The more rectangles I have, the better the approximation is going to be. With limits, if you put an infinite amount, that stands for infinity, if you put an infinite amount of rectangles between 2 points, it would be an exact approximation. Okay? Now remember, what we need to understand is, we need to understand here is in order to find the area, right, we can't find the area of a line. You can find the area of a rectangle, but that rectangle could be very, very small. Maybe the base of your rectangle might only be like 0.001, but it's still a base of your rectangle. Okay, it's still some kind of base, some kind of like width, right? It might be very small, but it's still a width nonetheless. All right, but one line, we can't find the area of a line. It has to at least be a rectangle. And that's what they mean by if we find an infinite amount of rectangles and make that area infinitely small as well, we would be getting a more better approximation of what the area under that curve is. So we're jumping back here to limits. All right, so let's jump back in here to figure out what are limits. All right, what does the function do as the variable approaches the given value? Not necessarily what it is at that value. What is it as it gets close to that? That's what we're trying to find out. It's not about that exact point. That's what we were talking about earlier with a secant versus a tangent. We kept sliding that point Q closer and closer and closer to P, right? But it never was P. We just kept sliding it closer, right? It was approaching P. The point kept getting closer and closer to P, all right? So here's example 2. I have f of x equals x squared. What happens as x approaches 2? Okay? Not what happens at 2. What happens as it gets close to 2? So what we're going to do is we're just going to plug in numbers for x and watch them get closer and closer to 2. Okay? So here is 2, right? The number 2. Okay? I'm going to plug in numbers on either side of the number 2. Okay? I'm going to plug in 1.5, 1.9, 1.999, right? I'm also going to plug in 2.001 and 2.01 and 2.5. So the point is I'm getting closer to 2 from this side, and I'm getting closer to 2 from this side. But either way, I can still get close to 2, and we want to see what happens as we do that. To save time, I'm going to plug these all in for you. All right? So remember, just so you can see, we're plugging the numbers into x squared. Okay? So when I'm doing this, I'm plugging 1.5 squared, right? 1.9 squared, 1.999 squared. I'm doing 2.5 squared, 2.01 squared, 2.0001 squared. All right, that's what I'm doing. I'm plugging that value in and getting an answer. And as I do that, when I plug in 1.5, I get 2.25. When I plug in 1.9, I get 3.61, and when I plug in 1.999, I get 3.9960. This side, it looks like it's approaching what number, right? Well, to me, it looks like it's getting pretty darn close to 4. So let's take a look on this side. If I plug in 2.5, I get this as my answer. If I plug in 2.01, I get this as my answer. If I plug in 2.0001, I get, again, what appears to be 4. So as I plug in numbers from this side, it looks like it's going to the number 4. And as I plug in numbers from this side, it also looks like it's going to 4. So as the limit approaches 2, it looks like our answer will be 4. So it looks like from the left, right? From the left, it's approaching 2, right? That's what it means. From the left, it's approaching 2, right? And it's approaching it at 4. As it approaches 2, right, we get 4. It's looking like it's heading towards the number 4. It looks like from left to the number 2, we're getting 4 as the answer. Over here, looks like from the right, as we approach 2, it looks like we are getting 4 again as the answer. All right? So the function must approach the same number from both the left and the right for the limit to exist. This is key. This is so big. You need to remember this. For a limit to exist, it must approach the same exact number from both sides. If it does not, the limit does not exist. This is huge. The limit must approach, again, the same thing from the left and from the right. If it does not go to the same thing, it does not exist. So our limit, this is what it looks like. All right, you're going to see a lot of this. The limit as x approaches 2 of x squared equals 4. And the reason why I know that it equals 4 is the number from the left we just saw approaches 4. The number from the right approaches 4. So because from both sides it approaches 4, the answer is 4. So in general, the limit of a function as x goes to some number a equals L. But x cannot equal a. All right? So we'll get to what this means in a minute. Take a look at example 3. All right. So, taking a look at example 3, this says we want to find the limit as x approaches 1 of all this. What happens to the problem as x approaches 1? So again, The only thing we are going to do is just plug in numbers and solve. We need to plug in numbers on either side of the number 1. Either side. Here's the number 1. So I'm going to plug in 0.5, 0.99, 0.999, right? It's getting closer and closer to 1. But I have to get closer and closer to 1 on the other side. 1.5, 1.01, 1.0001. So I'm going to take these numbers and plug them in to what we have. And remember, I'm plugging them into this here. So I'm taking the numbers and I'm plugging them in. So I'm going to be plugging in 0.5. But I'm plugging it in here. 0.5 minus 1 and 0.5 squared minus 1. All right, I'm plugging the values in. I'm going to save us the time and plug them in for you. When I plug in 0.5 into, when I plug 0.5 in here, right, that's what, again, this is what I'm plugging it all into. When I plug 0.5 in, we get 0.6. When I plug in 0.9, I get 0.503. When I plug in 0.999, I get 0.5. My first guess would be it looks like it's approaching 1/2, right? Looks like it's getting pretty darn close to 1/2. On this side, I plug in 1.5 into that. I get 0.4. I plug 1.01 into that. I get 0.49-ish. Again, when I plug in 1.0001, if you were to take a guess, it looks like it's approaching 0.5 or 1/2. It looks like it's approaching 0.5 from the left. It looks like it's approaching 0.5 from the right as well. So it looks like as x approaches 1 from the left, looks like I get 0.5 as my answer. It also looks like from the right, as x approaches 1 from the right, it also looks like it's going to 0.5. So my question to you is, does the limit exist? Does the limit exist at 1? The answer would be the function must approach the same number from both the left and the right for the limit to exist. So the limit of this is 0.5, because from the left we said it goes to 0.5, from the right we said it goes to 0.5. Since it goes to the same exact number, the limit does exist. So the limit is 0.5. Let's find the limit of any function as x goes to 2. So some function as x goes to 2, right? One-sided limits is what we're talking about now. One-sided limits. So this right here, we're going to look at some terminology and some basics to see what is what. I'm giving you a picture here, so why don't you take a minute to draw the picture. If it's easier for you, maybe you want to just pause the video and sketch a rough pic. All right. What we're going to do with this problem is we need to figure out from the left what x approaches, right? From the right what x approaches. That's what we're trying to figure out here. Okay, as we're looking at this. One-sided limits. If I'm looking at it just from one side, we want to see where it goes. If I'm looking at it from both sides, I have to do that to see if the limit exists. You need to find the limit from each side. The left side and the right. That's what we were talking about when we were doing substitution and plugging in numbers in our table. Right? From the right side, this little sign here, the positive sign stands for from the right. From the right side. So definitely jot this down in your notes so that you remember that means from the right. Alright? So I have a little arrow on our picture so we can see from the right side, what is it approaching? Right? We need to figure out what is x approaching. As x goes to 2, what do we get? Basically with these, what you're looking for is, what's it approaching? It's approaching a height, right? We're looking at the height. Where is it going at the y-axis? So when I get to 2, what does it look like it's approaching? It looks to me like it's approaching the number 1. Alright, and when we come back, I'm going to continue on a little more detail about right-sided limits.